talk about hydrodynamics without matching condition.
Okay, thank you. Okay, so this is working, right? I think you can hear me and the people from Zoom as well, right? Hopefully, yeah. So let me start just by thanking the organizers. So Francesco, Natalia, Eduardo, for inviting me here. Okay, I thank all the Italian organizers, I guess, for inviting me here. My first time in Florence, first time in this institute. And I'll talk about this topic, hydrodynamics without matching conditions, which is what I want to do. But you will see at the end that maybe I haven't finished it just yet. And let me just tell you some outlines. So this is kind of the what I'll discuss here. So start with some basis of fluid dynamics, discuss what are these matching conditions that were in the title of the talk, give some usual example of how first order hydrodynamics is derived from kinetic theory, and then try to discuss this possibility of deriving this equation without a matching condition, which means without introducing any reference equilibrium frame. Again, this is all from kinetic theory, and then I will end with my conclusions. So essentially, as you can see from the title, it will all be within the framework of kinetic theory. So I'll be discussing fluid dynamics essentially for dilute gases, right? So, but anyways, maybe some intuition, like often we do things for specific systems, but if the theory is universal enough, you can get some intuition about more general cases. I just want to have one slide about heavy ion collisions, right? So this talk will have nothing to do with heavy ion collisions, but I want to just give this as a general comment that, as many of you know here, we have this fluid dynamical modeling of heavy ion collisions. So this kind of picture emerges of what happens in a heavy ion collisions, where apparently the main assumption of these models, which appears to be confirmed by experiments, is that you were able to create a fluid of hot and dense nuclear matter or QCD matter at very early times, 1 Fermi over C. And then this very hot system just expands, and then the goal of these kind of collisions and models is to, study the fluid that is produced at the early stages with hydrodynamics, right? But as we all know, what also happened is that beyond studying nuclear physics using fluid dynamical models, we also ended up studying fluid dynamics as well from this kind of setting. So there are many toy models of heavy ion collisions that are just used to study fluid dynamics, as we saw in yesterday's talk by Chandrodoi. Like you have Bjorken flow, Gupsa flow, the Landau model, often just used as kind of experiments to study the solutions of hydrodynamics and their domain of applicability. So as it turned out, this kind of nuclear physics problem also triggered a lot of studies of fluid dynamics and developed a lot of knowledge in this direction. And I won't talk anymore about heavy ion collisions, so now I just discuss about fluid dynamics, which is the type of thing I'm trying to study. So as usual, there's always some definition, right, about what we mean by fluid dynamics, and it can vary from person to person. Nowadays, there are many formulations, in particular in the relativistic regime. But usually, I think this part, almost everyone can agree, there is supposed to be some effective theory describing the dynamics of a macroscopic system or of a system over long times and long distances. And it usually kind of has 3 fundamental ingredients, depending on how you count. So it's fundamentally based on conservation laws of energy, momentum, and charge, some equation of state, some notion of thermodynamics, and some hypotheses about dissipation, usually in terms of constitutive relations or dynamical relations, as often happens in the relativistic regime. If you just write down pure constitutive relations, you get a causal theories that cannot be solved in practice. And it appears that relativity demands some sort of dynamical relation or dynamical equation for your dissipative currents. When you talk about the validity of these theories, so often this is important in practice, right? You want to know when they break down and how they can be applied. So here I gave you some very vague sense of what we usually think should or is required, right? So there's some notion of small gradients. So you expect some separation of scales, that the distances over which your fluid variables vary in space should be much, much larger than your macroscopic scale. Like for a dilute gas, this would be clearly the mean-free path. So you expect the mean-free path to be much, much smaller than any macroscopic scale that your system has. And you can quantify this by the Knudsen number, if you want, of course. So this should be much, much smaller than 1. And I said I wouldn't mention heavy ion collisions, but I guess this is the main problem of heavy ion collisions, that we are not exactly in this regime, right? I mean, even a small Knudsen number in heavy ion collisions is already a large Knudsen number when you compare to any other fluid in nature. Maybe not any other, but ordinary fluids in nature, like water or air. The Knudsen number is very small. But in heavy ion collisions, we often have to worry about situations where this number is not small. And there's also this notion about the system being close to equilibrium, which is a little bit more vague. And this is, I guess, what I'll discuss more in this seminar. What do we mean by close to equilibrium, and how can this be in practice tested? So actually, I would like to get rid of this, but we'll see if I can succeed in this story. Okay, so let me start with ideal fluid dynamics. So this is the most basic theory. And this is essentially the discussion you can find in Landau's book or in most books. So in this case, you have essentially two fundamental ingredients. So you have conservation law as usual. So here I wrote down some conservation for some net charge and for energy and momentum. And this notion of local thermodynamic equilibrium, which for at least in this talk, I mean, I'll just use that there is a frame or a local reference frame where the conserved currents take the form of global equilibrium, at least at any time. So then T mu is just given by, in this frame, by this diagonal form, energy density and pressure. And this pressure, of course, is given by some equation of state. So it's a function of this energy density and your charge. And also the particle current and the entropy current also take this form where they just have the time component and everything else vanishes. Now this procedure defines a velocity field, right? So these currents are connected to the currents in the lab frame by a Lorentz transformation for a given velocity. And so, yeah.
If the fluid is accelerated, even in the left frame.
Yeah, of course, here this is like a tangential Lorentz boost, right? You just do a constant velocity, just follows the motion of the fluid at that time, but you don't actually follow the velocity. I don't know if I... Yes. Okay, no rotations. There's no rotations here. Yeah, you're right.
Even in the local frame, you may have non-diagonal, although they are suppressed by...
True. So this here would assume there is no such effect. You're right. True. But in general, I mean, he's right. So
it depends on, yeah, but then it depends on how you define the dynamics. So, but if you have strictly speaking, if you have a fluid, then which is spinning, then you go to the local rest frame, so you follow the...
Yeah.
Then in this case, the local observer measures some...
True.
Anisotropic, first of all, anisotropic pressure.
True.
Then also double diagonal.
Yeah. So your famous paper with the vorticity square term as well that can appear in equilibrium. Yeah.
You can act, so you can infer this not just from just from the fact that you break symmetry. You may have some idea.
Yeah. So I agree. But here this simpler picture will So
you can see that this is the second order effect.
Yes, in gradients at least. And then, so from this picture, then this very simple form of this ideal conserved currents emerge. So they just have simple decomposition in terms of this four velocity. And of course, if your effects are considered, you can have correction to this even in the ideal limit. I agree with that. And here, this four velocities is very well defined. So it just follows essentially everything. It follows the energy, the net charge, the entropy. It's just everything moving together. And from the equation of state, so you just, if you take this energy density and net charge density in the local rest frame and calculate the entropy from an equation of state, you can define the inverse temperature and the thermal potential just using thermodynamics. So here, everything is kind of well defined. But of course, the problem is that this doesn't really exist, right? I mean, in ordinary fluids, you cannot ever find such a frame. It doesn't exist. So you always try to add dissipation and correct this kind of, or treat dissipation as a correction to this kind of physics. So the idea is, if you take a dissipative fluid, there's an I missing here. Of course, the conservation laws remain, they're general. You're not going to break this fundamental physics, but you try to correct the general form of these conserved currents, and you can see here that essentially you just write them, you just write corrections to this local equilibrium form. So the net charge current can have something proportional to the velocity as before, but it's also some correction which is due to diffusion. And also the T mu, you have this equilibrium part here, and you just add all the possible contributions that could exist. And in this case, this H mu represents some energy diffusion, and pi mu, the shear stress tensor that we know very well in heavy ion collisions. And here there's just some notation. We define this projection operator, and then this already illustrates my metric convention, which is mostly negative. Okay, so the problem here is that you have an expansion around this equilibrium state, but it doesn't really exist, right? I mean, I call it a fictitious equilibrium state in the sense that these conserved currents were never in equilibrium in the first place. So I'm not thinking of a problem where the system was in equilibrium and I perturbed it out of equilibrium. I'm just thinking of the motion of a fluid where all that we know are these off equilibrium currents, and it was never in equilibrium in the first place. So this kind of expansion, you're kind of imagining that there is a local equilibrium state, so some state of this form, right, that is near, that is close to these kind of conserved currents, and then I'm just correcting around it. So that's kind of the logic. And in this sense, there is some arbitrariness in this choice of equilibrium, right? So in other words, before, I could define this velocity as something following energy, charge, and entropy, everything. But out of equilibrium, these different quantities, they flow in different ways. So from this one definition of velocity here, you can get several directions out of equilibrium. And also, technically, there's no equation of state to define these thermal quantities. Just to mention, there are, of course, well-known two kind of special directions in this formalism. So if you take your out of equilibrium energy momentum tensor, you can still define a direction related to the flow of energy. So this is some eigenvector of this current, and then the eigenvalue is the energy density in the local frame of this velocity. And there's another special direction related to the flow of charge, which I call here V mu. So this follows the flow of particles, and this n is the charge density or the particle density in the frame where this V mu is 1000. And as I mentioned, these two velocities now, in equilibrium, these two velocities are the same thing, if local equilibrium exists. But out of equilibrium, in principle, they are different, and the difference is proportional to the heat flow, so to first order gradients. So if the gradients are small, it's supposed to be a small difference, and everything is under control. If the gradients are large, then of course this is a big difference, right? Mm-hmm. In what sense? How do I get here? Yeah, so there are many steps actually. So so here by heat flow I mean the difference between this charge flow and the enthalpy flow. So this times epsilon plus p over n, and energy diffusion, right? So they appear in these decompositions, and if you just calculate this difference using, using these definitions, you get something like this as long as you throw away higher order terms in gradients. And then this P is kind of defined as a thermodynamic pressure constructed from this energy density. So you can just carry out this calculation. To entropy. Yes, it relates to entropy. Yes. Okay. So how do you define, let me talk about these two. There are two famous definitions of this equilibrium state that we usually expand around, essentially do by Landau and Eckert. So essentially, it's down below here, but you may start with a definition of velocity, which again, in principle, could be anything. It doesn't mean that it makes sense, but it could be anything. But there are two natural choices, like either you choose this direction of energy flow from your T mu, which is what Landau did, or you can choose a special direction from your charge current, which is what Eckert did, or you can do anything else that you want. So again, I mean, you can do anything, but you always pay a price because in principle, it's arbitrary. But as we know, this will end up working out as the leading term in an expansion that will be truncated. So of course, the choice of the first term of your expansion will matter. But let's say if you're just solving the Boltzmann equation and you get your T mu and mu numerically calculated, you can just do this decomposition any way that you want and it will work. Okay, so first you define your velocity. You can have this Landau definition, which we use a lot in heavy ion collisions, just because we don't have a net charge, usually at high energies. Or the astrophysics, they prefer this one, the Eckert definition, since they have a large baryon current. And then you can go here and define your temperature and chemical potential in this way. You can essentially calculate these two physical things, which are the energy density and the charge density in your local rest frame. So given some velocity. And then you can just take an equilibrium equation of state with these two quantities. So, and calculate temperature and chemical potential as if the system were in equilibrium. So this gives you a prescription to get a temperature and a chemical potential for thermodynamic relations. And then the pressure just comes out from the Euler relation, like this here. So as was discussed yesterday, this temperature and this chemical potential, I mean, they don't have to be, they won't be what you measure with a thermometer or anything. I mean, this.
The whole idea in this method.
Yes.
That you take N and epsilon. Because you are choosing U particle, right?
Yes, yes, yes.
Then you take a function which is purely thermodynamic, which is the answer is a function of N and epsilon. But then epsilon has not been defined thermodynamically, but they've been defined with this arbitrary velocity.
Yes.
Then you enforce this relation, which would be not, which is purely thermodynamic, both only at equilibrium.
Yes.
Right. So in this case, it seems that you are making an assumption about the validity of this thermodynamic relation.
Yes.
So beyond.
Yes. Yes. I agree. I mean, it's more right now it's a prescription, right? And the thing is, I mean, again, you can always do it, but then the problem is that later you will try to correct this, like use this prescription and its gradients to correct this mistake, right? So you never get the actual velocity or the actual temperature, and then later these terms are supposed to make corrections that make it more physical, let's say like that.
What I'm saying is that there is another assumption, not just the choice of use time.
Yes.
But here there is an assumption.
Yes.
It's not strictly speaking, it's not verified. For instance, you can find exceptions when you study the which is the point.
Yes.
If you write relation, P naught equal minus epsilon plus E0 S0 plus.
Yes. Yes. Yes.
Strictly speaking,
only in equilibrium. Yes. Yes. It's a definition. Yeah. Yeah, it's a definition, but I mean, we assume, but the assumption is that thermodynamic holds. That's a real assumption, yeah.
Definition of P naught.
Yeah.
But P naught is somewhat related.
Yeah, but the thing is, so for example, here we define this P naught, this pressure, but of course, the real pressure of the fluid is this P naught plus a bulk viscous correction. And then the question is how this, and the bulk viscous correction is written at first order in gradient. So the question is how good is this approximation, the truncated approximation at the end of the day, right? It's a definition. Yes.
You define P naught.
It's a definition, yeah, I agree.
I'm saying equilibrium, I know that I can read off the true temperature, whatever that means. By looking at some components of the stress. Do you look at the components of the stress read off your if I give you the stress tensor and you know how you want to define the temperature and velocity from the stress tensor, then you can just do it.
Yes.
Right? So if you changing these definitions just means that you're sort of again, the theory that the on-shell stress tensor would be the same, whatever definition you have.
Again, I mean, if gradients are small, because it's yes. So but I mean, I think in practice, let's say if everything works, they shouldn't matter, right? But often we take these theories and we apply them in situations where we are pushing a little bit the boundaries where, so I think that's the concern that some people have, and I have them too, but still, I think this slide is exactly what I'm trying to get rid of. I mean, in this talk, you'll see if I succeed or not, but like I would like to not have to define this arbitrary state that we expand around.
But the fact, sorry, but if the function S naught of n to the epsilon
Mhm.
is assumed to be the one which is
Exactly, it's got the fluid in equilibrium.
the global.
Yeah, exactly. It's assumed to be. Even though formally you could take anything, but that would just be crazy, right? It's better if you just take the real thermodynamic contribution. Okay, so this is essentially the two pictures, Landau and Eckert, right? But you can do more, even though I would know how to do them in practice. Nowadays, this issue became a little bit more complicated because of these generalized first order theories, which were derived by Benfica, Visconti, and Noronha, and then later also by Kovtun, so this B, D, and K theory, where essentially they only work if it's not Landau and Eckert, right? So you have to choose a matching condition which cannot be neither this one or that one. It has to be some other matching condition. And in this case, essentially, like I gave you some specific example where the temperature and chemical potential was defined from the full densities in the local rest frame, but you can also do like just take part of them to define these quantities. And so you can also have off-equilibrium corrections, non-thermal corrections to these densities, as you do usually for the pressure. And this BD and K theories only work in matches where these guys are not zero. You have to let them exist if you want a causal theory. So this kind of trigger, like, more studies about matching conditions and things that are not Landau or Eckert. But okay, let's see how this happens in kinetic theory. So first I will start with the usual derivation of hydrodynamics following a gradient expansion. So essentially the derivation of Navier-Stokes theory from the Boltzmann equation. So the starting point is, of course, the Boltzmann equation itself. This is the momentum distribution function, and this is the collision term, which contains all the microscopic information here, but just essentially cross-sections, so collisions between particles. And you look for solutions. So of course, this term, it goes as 1 over L, so it's a gradient of F. And the collision term goes as 1 over the microscopic scale, which contains the mean free path, or the cross-section. And so you want a solution where this F varies extremely slowly in space. So this guy here is very, very small compared to the mean free path. And this is the interpretation of this hydrodynamic regime. Like you try to find solutions where essentially this guy is supposed to be very, very small, right? And so you have F should be close to a state where this collision term also should be very, very small. The way that you implement this is usually some sort of, this is called formally a Chapman-Ensworth expansion. These are the people who did it first. They generalized the Hilbert expansion too. And I think this was the first derivation of Navier-Stokes equations from a microscopic theory back in the day. So then you rewrite the Boltzmann equation like this, and you just introduce this kind of small bookkeeping parameter to remember that these terms are supposed to be very small. And here I separate them into like a time-like derivative, a moving derivative of F, and a space-like derivative of F, and this is the collision term. And you look for some solution like this, right? Some powers of the small parameter epsilon, which here is supposed to represent this Knudsen number, or this ratio between these two scales, which is supposed to be very small. And formally, you also have to do an expansion of this time derivative of F, right? Now, this I'll discuss in this talk. Usually, this very simple example of an interaction, like a lambda phi 4 self-interacting scalar field theory, with classical in the classical massless limits. So essentially, the cross section just goes as 1 over S, where S is the Mandelson variable, and this G here will represent always the coupling, right? Lambda square. So in this case, so I use this essentially because this is one case where we actually know the spectrum of this linear collision operator. So if you take the Boltzmann equation and you expand it around equilibrium, you get this linearized collision term instead, which contains information on some equilibrium state. So it's given by this formula. And for this specific cross-section, 1 over S, you can actually calculate the eigenfunctions and eigenvalues of this operator. So it's just given by this formula here. So they're given by this reducible tensors times some associated Laguerre polynomial. And the eigenvalues are this chi and L. So N and L vary from 0 to infinity. And in this specific limit, it's very convenient because you can calculate pretty much everything analytically and exactly, right? So, yeah. Sorry, so I not, where? Box, lower. Ah, sorry, true. I did not define it. So this is a thermodynamic integral. Essentially goes as T square, like thermal mass. It's discrete here. Discrete spectral, yeah. It goes just, N is just a quantized 0, 1, 2, and so on. Yeah. So of course, I mean, a comment. So this spectrum is not related to the eigen modes of the Boltzmann equation, because if you look at this equation, here you have the linearized collision term, and if you want to solve for F, there's a 1 over energy factor. So if you want to actually know the eigenfunctions, it will not be this discrete spectrum, it will become continuous, like a non-gapped, as was shown by Lorenzo there in the back. But luckily, this one is gapped. I mean, it's discrete, and you know all the values here. And this is like a thermal mass, like a T square contribution. And they're all negative, as expected, and so on. So if you know this, you can actually solve this rather simply. So again, coming back to this order by order solution, the 0th order solution is just the one which makes the collision term vanish. So as I said, this is supposed to be very small because the stuff here is very small. And to lead the order is just 0. So then you get as a leading correction contribution, this local equilibrium distribution, which I just call F0, but it's a Boltzmann here. It's a classical system. It's like a Boltzmann distribution. And this is where temperature and chemical potential appear in this kind of expansion. And at this point, it could be any temperature and chemical potential, just two parameters. Then to first order, you have to solve some equation like this one. So there's some notation here, and this is a mistake. There's no 1 here. This phi is just the first order correction over equilibrium. So that's what appears. And so on the right-hand side, you get exactly this linear collision term applied to this function phi, which is what you want to find out. This has to do with your first order correction. And on the left-hand side, you usually get just gradients, space-like gradients of your fluid dynamical variable. So you get gradient of chemical potential over temperature here. This L1 is, I just wrote this energy dependence in terms of a Laguerre polynomial, but this is just some energy dependence that's hidden in this notation. And here you have the shear tensor, which is just has to do with derivatives of velocity. In this case, there is no bulk because I'm doing the massless limit. So in more general case, there will be one term here which has to do with bulk, just a purely scalar term. But since I'm in the massless limit, this term doesn't exist, okay? So if you want to solve this, you have to invert this operator, essentially, and get phi. And this is what you get. So your first order correction will be some homogeneous solution, essentially something which vanishes when you apply this operator, plus this kind of guy here, which is the particular solution. And in principle, since I know the eigenfunctions of this operator, I can actually solve this analytically, okay? Now, this homogeneous solution is very simple. It's supposed to be just a constant times B mu, P mu. B mu is another constant, or momentum-independent quantities. And these are just the two contributions that make this guy vanish. They are conserved in collisions, right? So you know that it only has this form. And in this case, and they are actually fixed by these matching conditions. So in kinetic theory, they appear as something like this, like some integral of delta F should vanish. So if you're not familiar with this, like if you put z equals 0, just integral of p mu delta F equals 0, this would give you the Eckert condition. And if you put z equal 1, so just some integral of energy times this 4 vector, it will give you the Landau condition. So this is how, so here we're trying to do like a generalization of these two matching conditions by just putting this, interpolating them by this z parameter, which gives you a power of energy. Okay, so what does this mean? So let's just say you take the part of the solution, which is the equilibrium plus this homogeneous solution. This is two corrections. Let's forget everything else that would come from the gradients here. So what you see is that it looks like this. So 1 plus the homogeneous solution And if this is small, which it should be, so you're still thinking that this homogeneous solution is kind of first order in gradients, so it's supposed to be a small correction, you can just kind of exponentiate it back. You can treat it approximately like some exponential of A plus B mu K mu. And then at the end of the day, you could just incorporate it back into your equilibrium state. So you can, if this is small, you can essentially think of these two parameters in your homogeneous solution as corrections to chemical potential and to the thermophore velocity, right? So this freedom in the homogeneous solution that you have here when inverting the first order operator has to do with also some kind of freedom you have in changing your temperature and your chemical potential of your local equilibrium state. And this is what we fix by these matching conditions in this kind of derivation of the Boltzmann equation, okay? Of course, this is true if this is small. If this is large, then this picture will not be exact. So okay, once you solve for this F, you can just insert them in T mu and the conserved currents and get constitutive relations for your dissipative currents. So the answer is in this red box here. And in this case, since we are in this massless picture, there will be no corrections no dissipative corrections to the particle number and to the energy density, regardless of your matching conditions. So they just all be zero anyway. But you can see here that your diffusion current, so this is the net charge diffusion or the particle diffusion here, and this is the energy diffusion for current. They all go with the gradient of the thermal potential, as is usually the case. But the transport coefficient that relates them depends on this choice of matching that you employed. So this is encoded in this parameter z, which could be anything from 0 to infinity. So as you can see, if z is 0, this should give you Eckert. And indeed, in Eckert frame, this guy vanishes. That is the Eckert condition. You kill any particle diffusion. It just doesn't exist. And if this z is 1, you are in the Landau frame, which is defined by killing any energy diffusion. So then this guy is just 0. But in between, you can have several configurations where you have these two guys, and the transfer coefficients will have a dependence on this choice of frame, right? So yeah. What was Z? Okay, so this new, wait, blah, blah, blah. So this new is supposed to be this correction. Yeah. So the change, so the definition, so the condition, wait. The condition is supposed to be this one, right? Right here. So you're saying that some integral of delta F should vanish, right? And if Z is 0, this integral is exactly the definition of that new mu current, right? And if Z is 1, this is exactly the definition of H mu, right? And so that's why they have to disappear. And you have more corrections in the scalar sector, but since it's a massless theory, it doesn't matter here. Yes? Sorry, which? This one? Yes. The sigma mu nu, sorry. What is the definition of u mu? No, u mu is just whatever parameter. It's actually, it will later be fixed by this condition here, right? So it started just some parameter in F0, and then later it is fixed by some condition like this one. But later, always later. Well, I mean, yeah, I guess you can say like that. You specify it later. Because u mu is a solution of the conservation laws, and then it will matter if for the solution of u mu, if this h is 0 or this nu is 0, right? So by changing these two guys, you're changing the solution of the velocity that will come out from these conservation laws, right? Z has to be, it cannot be anything because this integral must converge. So Z cannot be arbitrarily negative. I think -1 is the minimum value allowed. But it cannot just be -10. Then it won't really make any sense. And you can see that, yeah.
summarize the logic. So here you have this
Yes.
general solution.
Yes. Yes. This
General
one.
solution
Yes.
is fine. You
Yes.
have phi homogeneous, which is in general A plus B.
Exactly. And you don't know what A and B are. Yes.
And then you fix them by using the matching.
Exactly. Which in the Boltzmann equation always appears like this.
After applying
Of this procedure. So this procedure gives this result. And in general, if it's not in the massless case, this A would also be fixed by other matching conditions in the scalar sector. But here, everything is zero, it doesn't matter.
yes, this corresponds to essentially to the local equilibrium of some. Yeah, okay.
So yeah, I mean, I know it's not the most comforting thing to have transfer coefficients that depend on a parameter. But again, this is the dial you have of changing your velocity definition. It will change also your transport. There's just no way around it. I mean, like it or not. So as I said, I don't like it. So I'm trying to not do this. Okay. So is there a way then to do this without introducing this fictitious equilibrium state? So you see that even when you do it from the Boltzmann equation, it tends to appear in several forms as these three parameters that you have to fix somehow. So that's what I'm thinking about recently. I don't know how to do it in general. So here I will show you one explicit example where I managed to do it somehow. And then you see at the end what I get, right? What kind of theory I get and what are its pathologies. So again, Boltzmann equation, I'm repeating some formulas here, so I'll do everything in the Boltzmann equation. Again, for this simple cross-section corresponding to this simple interaction picture, so it just goes as 1 over S. And I do this simply because it's a situation in which I can do the calculations, right? Analytically and explicitly. So I cannot do, what I will do next will be specific to this case, okay? And what I will do is essentially not try to solve the Boltzmann equation itself using a gradient expansion, but I will try to solve moments of the Boltzmann equation using the same logic of a gradient expansion. So I'll just take the Boltzmann equation and I integrate it in momentum. I multiply by 4 momentum, integrate it again. So these two just give you the usual conservation laws that you are used to. But I can just keep doing the same procedure on and on again, like getting higher moments of the Boltzmann equation, which will give me not an equation for n mu and t mu, but for other higher rank tensors, right? And the idea is that I try to do something already in terms of these hydrodynamic fields and not the actual F. So then, as I said, you get something like this. So the first 2 moments are conservation laws, which here I use this, I just call them J. Right? I regret this, I mean, yesterday while I was preparing the slides, but I use this notation here. So J mu is what I was calling before N mu, is the particle current. J mu nu is what we usually call T mu nu. So here I just give this notation, which is very regrettable. And first 2 moments of the Boltzmann equation are conservation laws. We use them already, we know them very well. And the higher moments are just equations of this form, where on the right-hand side, you have moments of the collision integral, right? And these have to do with this kind of non-hydrodynamic degrees of freedom, like the quasi-normal modes, which are gapped. They're not hydrodynamical variables, but they are gapped modes. And the reason why I'm doing this for this specific interaction here, and is because for this interaction, I can calculate these moments of the collision term exactly in terms of F, without relying on any approximation whatsoever. And so, for example, if you calculate this one, you get this expression here, which is an exact expression for this collision term. So in terms of the particle current and the energy momentum tensor, this A, I think I defined on the next slide, this A is just the integral of F, is the 0th moment of the Boltzmann equation, if you want to call it like that. And so the equations, they look a little bit like this, right? So again, sorry. G has to do with the coupling of the microscopic interaction. It's essentially lambda squared up some factor. Okay, so then I get this kind of equation like this, and this is exact. There are no approximations here. And you can keep doing this forever, but I wrote down just the first 2 non-trivial terms of this expansion. And again, this is not general. This happens for this interaction, but you can see that everything kind of comes out in terms of these moments of F. This, of course, is a lucky coincidence of this interaction. In general, it could be more complicated. And the right-hand side, you can see they all come from the collision term. Always this G will appear, which is the interaction strength, and so on. So my idea would be to actually apply a gradient expansion to this set of equations instead of doing it to the Boltzmann equation directly. So the logic would be that on the left-hand side, we have gradients of moments of F. And in the hydro regime, I expect these moments to vary extremely slowly in space and time. So I'm thinking that these guys here should be very small. And on the right-hand side, I have something that comes due to interaction. It contains the coupling here. And so it's supposed to be something that kind of goes with a microscopic scale, G over T. Yes? No, I mean, the kinetic theory is already this leading order effective theory. So in principle, this is valid for small g. I mean, in the sense that the kinetic theory description. Yeah, go ahead. Yeah, true. Okay. True. Yes. That's true. So I'm assuming that the starting point, the Boltzmann equation, is a reliable effective theory for this theory. But you're right. I mean, they will all be proportional to G all the way down. This is the only thing I can tell you for sure. Yes. So G will appear in all of them. In terms of moments, let's say. You can not by a recursion, but you can actually get general expressions for them if you want. But you can also do them one. But from what you see here, there's no need to compute them beyond this moment here. But you'll see why soon. Okay, so then let's try to solve it in this way, right? This is small, and I try to find some perturbative solution. So actually what I do is I will rewrite this almost as if a constitutive relation for the moments. So T mu, here J nu alpha, will be given by this expression here. So again, I'm just taking this guy and exchanging putting this guy to the other side. So as if it's J mu is given by this plus some gradient correction. And then this guy, which appears up here, is also given by this leading expression plus some gradient correction. And you can go like that forever and ever. And what I'll do here is I just iterate, right? I just take this expression, put it up here, whatever is down here, put it up there. And if you do that, you will get some expansion in powers of gradients of these currents, J mu nu, and this scalar moment A, right? If you just keep doing this forever and ever. Yes? Yes. So you can count in powers of epsilon. So here I'll do, I think, a little bit. So, okay, I'll comment on this later, but there's two ways that you can do this. One is more formal. The other one is more, there's some implicit resummation implied. So, but essentially what I would do is just reiterate this equation and get a gradient expansion. So then you get something like this, right? So T mu is given by this kind of correction without any gradients, plus this term here, and something that has to do with G minus 2 derivative squared, which you can also write down if you want, but here I just omit this term. And the interesting thing is that at leading order, if I throw out this first order contribution, what I get is that G mu or T mu is equal to this here. And you can almost recognize this as the ideal fluid form, right? But instead of a for velocity, what is here is the particle current, right? Sorry?
Turns out to be expansion in language.
Times gradient, so like a Knudsen number.
Yeah, no,
Yeah.
I understand. But G was supposed to be small.
Yeah. True, correct. So of course this works when G is small, and here G is supposed to be large, but large compared to the gradient. So this just means that for a gas, it's just harder to find the ideal fluid limit. You need to look at longer scales than if the interaction strength is. You see what I'm saying? So gases are weakly interacting.
You have a special regime.
Yes. G is
The fluid number is small, but it's so small that it should prevail over the fact that G also.
Exactly. This is correct. But again, this just means that it should be harder to get the hydro limit for gases than for interacting fluids, right? This makes sense to me at least. No, it is like, you know,
because yeah, kinetic theory. Maybe it should be, that means that we have a weakly coupling, weakly coupling. But kinetic theory cannot apply if you have a strongly coupled.
well, I mean, so here the cross section goes with this G, right? And here the cross section goes with this G, is G over S. Yeah. Hmm. Yes. Hmm. Yeah, yeah, yeah. Yes, exactly. So let's say if the Boltzmann equation holds for any value of G, I can do whatever I want. But of course, you're just pointing out that in principle, when it was derived, assumptions were made on the value of G, right? So just keep this in mind. I think it's okay. Yeah, that works, but yeah, yeah, yeah. Yes, yes, and but yeah, yeah, exactly. I can always find a gradient where this will work. Yeah, exactly, 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 exactly. So there'll always be a value of gradient in which this will hold. Maybe it will be extremely small and useless, but as I said, academic exercise. Yeah, yeah. Yeah. And hydro, I mean, the hydrodynamics has this all the time, right? So when you take the continuous limit, right, or to define a fluid, you're saying that every fluid element has zero size. But when you zoom in, it's supposed to be a thermodynamic system large enough to encompass a lot of particles. So you always assume that they are actually you can define a scale which is in between these two. So it's large compared to something, which is microscopic, and small compared to something, which is macroscopic. And you live in between these two scales, right? So this here is essentially how this kind of formalism returns me the ideal fluid form, even though I didn't make any mention of equilibrium. So if you, for example, define a velocity from this, oh, here I put n mu, I forgot to change it to j. You can just write this j mu in this form, which is the usual form of a local equilibrium fluid, even though, again, I made no reference of such a state here. And these quantities here, this n, which comes from the magnitude of the particle current, and this a, which was the zeroth moment of the Boltzmann equation, if you were to calculate them in equilibrium, they would have this kind of form. So a, if it's in equilibrium, right, would be t squared, and n is t cubic, and these quantities would actually match what you would expect for energy and pressure, right? Even though I don't have to make these assumptions here. So this, yes. 2 slides. This, one more or one more? Ah, okay. Here. Yes. Yeah. So it would just be that so let's say, if you recall, to zeroth order, the idea is that the collision term is very small, essentially zero, right? Because these gradients are very small. So essentially, the zeroth order solution is just this vanishing, right? For this to vanish, this guy has to be approximately of this form, and G would also go away. So this is kind of how this equilibrium thing happens, appears here in some form. And then to first order, you have to get this guy and approximate using the below expression, and just keep doing that until you get tired, I guess. So I don't know if I made myself clear, but in the end, you get this kind of equation. And to leading order, you get something that looks like an ideal fluid. And this kind of system appears, I mean, this seems a lot like Eckert. Even though I made no assumption of an Eckert frame, this seems a lot like something like an Eckert frame. But again, it just came out this way. You don't make an assumption about any equilibrium state. Again, this is the zeroth order term, which should match something that you expect in an ideal. So then they should, in principle, they should all coincide. But again, the point is I didn't really make any reference to an equilibrium state, right? No, but again, uh, uh, it's true. So here I don't mean this V mu as fixing an Eckert frame. I just mean it as a direction calculated from a conserved current, right? So it's just a re-expression of the other guy in this way. So it's not a choice of frame. It's just a way to express this in terms of a variable that we know, which is the Eckert velocity. Yes, if it were an ideal fluid, you could change it to another velocity and you get the same result. Okay. So, and then to first, so this is fun. So this to first order, you get an equation like this one here, right? Which is, if you look carefully, I mean, if this is an equation of motion for these three guys. It's harder to see just by looking, but you can actually, so this is what you're solving for, and you can extract from this tensor here the information that is missing, right? So if I go back a few slides, from the conservation laws, I should get J0 and J0I, right? Or sorry, J0 mu. And so, and from this equation here, in principle, I should get this the missing information, which is the spatial part of J, of the particle current, and the off diagonal, the spatial part of T mu, and this scalar moment. So this gives you kind of a dynamical equation for these fields. And of course, this here, again, there was no mention of an equilibrium state. The only assumption here is that gradients are small. And equilibrium or not should come out for free, I guess, if the physics is right. Yes. Pretty much, yeah, I put this. So essentially, this side here, there's a source term, which is T mu minus the leading order correction to T mu. So this, if you think of this like an equilibrium thing, this would be T mu minus T mu equilibrium, even though there's no equilibrium here. And then this guy is just going towards this source term, right? Now, you can take this equation and put it in a more familiar form if you desire. So again, you can come here, and again, you can define like an Eckert velocity, I mean, just from this current, and you can try to project out what we usually call the shear stress tensor. So again, you don't have to do it, but if you do it, just to put this equation in a familiar form, you get something like this, which is very similar to an Iso-Stewart theory, right? So if you look here, this will be the usual Navier-Stokes term. So this is the shear tensor. This here is already an explicit expression for part of the shear viscosity. So this, and this is the full Navier-Stokes solution. This is the relaxation term that we usually get. So the first three terms is just something relaxing. It's just pi mu relaxing to the derivatives of this current here. And all the other terms are just nonlinear complicated terms. But there's no temperature, there's no chemical potential. All that will appear are these fields A and N, which is the magnitude of the particle current, right? So funny enough here, Iso-Stewart theory appears as a first order theory. It's not a second order, because here all I have is first order in gradients of T mu. N, exactly, is the square root of this guy. No. So this U is just a direction of N, and this N is just the size of N. So it's not a matching dependent thing. It's just quantities that exist in real life. So of course, I mean, since there's no equilibrium state, all that I have are grades of T mu. So in principle, derivative of pi and derivative of anything else comes on the same footing, right? So to get the usual ordering that we are very intuitive with, you have to decompose in this form and then realize that this guy comes as a gradient of this guy, and then you can start reordering the size of these things. But up here, there's no velocity, no nothing. Iso-Stewart is a first order theory to some extent, right? Okay, now it doesn't end well. So, so up to here, I was very excited. If you project with the velocity and the projection operator, you'll get an equation for heat flow, which also looks like Iso-Stewart, but you can do a final projection, right? You can also take this equation and project with, again, I call this U mu, but you can understand just as as that, right? I mean, it's not a choice of velocity. It's just the direction of this current. And then you can get this kind of a scalar equation, which involves this variable E and the variable A, which is this non-hydrodynamic variable that just appeared when doing the calculation. So you get some equation like this here. And you can then also combine it with a projected equation for T mu nu. Here again, I call it T mu nu, but in the previous notation, it's J mu nu, which I regrettably use this notation. And if you combine these two equations, you will see that the equation of motion for A is unstable. It will be a relaxation equation that blows up. Like it has the, if you like it, it will have the wrong sign of the relaxation time. So this theory is unstable. If you perturb it around equilibrium, it just blows up. So yeah, that's bad. So usually, as someone who does heavy ions, we are very practical. We want theories that work, right? And this one doesn't, even though it was looking very promising. There are a few things that one can do. So one can just go higher order. So you can just put the second order corrections in gradients. And then you will have, instead of a first order equation for E and A, you get a second order equation in time. And then it appears that this will be stable. But then it's already a very complicated theory. Because I cannot just improve A. I have to put the new terms for all the currents, right? So this theory is unstable. Okay. So this is kind of where I am right now. So that's just come to my conclusion. So usual hydrodynamic formulations, they depend on a choice of equilibrium frame, which is in principle arbitrary. And these conditions can even affect the transport coefficients that you derive. And in kinetic theory, you can see this rather clearly, right? Usually shear is the only one that is matching independent, but anything that comes from bulk and heat flow will depend on a choice of matching if you do it in the Boltzmann equation. And using the method of moments, I showed you was this possible to implement a gradient expansion for the conserved currents, not for any F or anything else, and without the direct need of introducing an equilibrium frame. So, and then here I showed that, the first order equation from this framework, but from the last slide, as you can see, these equations are unstable around equilibrium. And so there's still some work to be done. And of course, I'll take any help from anyone here who knows the answer. So thank you very much. To the epsilon slide, okay. Yes. 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 Mm-hmm. Yeah. Yes. The separation of moments is not. Mm-hmm. No, I don't think I understood the. Yeah, but maybe I can make a comment that I forgot. So there's one thing that I did here, which formally implies in a resummation that when you start iterating these equations, you can plug like everything up here, but in principle, formally, you can also take this J as the leading order expression in terms of the particle current. You don't have to put the full T mu nu there. And if you do this, you get BD and K theory. You actually get BD and K theory. You don't get an iso-Stewart-like theory, but it's still unstable. So this will not fix this problem if you do a more like formal perturbative scheme. I don't know if it's actually with your question, but otherwise we can discuss it in the coffee break. Yeah. Okay, to be fair, this is also why this is a very convenient example. So in a conformal system, you get the equation of state kind of for free. So epsilon will be equal to free. If you define a pressure, it will be, 1/3 of epsilon anyway. But in principle here, there's no mention of an equation of state. You just have T mu nu and the particle current and nothing else. Equation of state appears at best when you do this here. No, I missed it here. So this A, which you solve, if it's in equilibrium, then the thermodynamic relation will start to appear. But in principle, there's no equation of state. There's just this variable here, which you solve for. And,
This is defined as the integral
of F, yeah.
two.
So we use the opens.
Yes.
But in order to aggregate the opens, we use the FK.
Yes, that's one way. No. So this is the trick. So when I integrate the Boltzmann equation, so I integrated the Boltzmann equation and I got rid of any mention of F. So through all of these moments are integrals of F, but I solve for them. I don't solve for F. No. There's no fluid velocity. There's no equilibrium. Yeah, just keeps, exactly, exactly, and keep solving, and that, yeah. And of course you can see, don't, no, and no temperature as well. No. Yeah, it's hard to see, right? I mean, so the problem is that when you do this kind of situation, so again here, yeah, okay. So you have an equation for energy and E dot and A dot combined, right? So also in the conservation law, you have E dot here. And so when you combine them both, you will get just an equation for A, which will have the wrong sign for the relaxation term. It's like A dot minus something times A. And so instead of relaxing to Navier-Stokes or whatever, it just explodes. True. Yeah. It's not so obvious, but I guess the most obvious way to see this if you just take the full equations like this one and just perturb around the equilibrium. So just consider some state which has constant J0 and constant J0 mu, and you perturb around it. And then you see that this A will explode unless it is exactly the equilibrium value. But any perturbation around the equilibrium just explodes. So yeah. Yes. Yes. I didn't try. Yes. Yeah, so this is one option. So maybe there's a specific choice now. So maybe a good choice of frame would be one where maybe I can kill this instability. That's one possibility. But I couldn't find it. I couldn't find it. But my strategy, yeah. But my goal here was to derive these equations first. Let's assume they were stable, which they're not. And then by solving them, trying to understand if there is an optimal frame choice, which the system is trying to get, right? I mean, there's some optimal dynamical, way to get the hydro frame. But of course, I do believe that being close to equilibrium is something not completely fantastious and fictitious. I mean, it should happen in real life in some situations. I just wanted to know how to obtain this without initially assuming it, right? Just as a dynamically getting there. But from these equations, it won't happen, right? No, not the way it is right now. But yeah, I mean, I have no idea. I mean, so from this interaction, we just have elastic collision, so there will always be a conserved. The particle number will be conserved, and there's nothing I can do about it. And for more general interactions, it will be a little bit more challenging to calculate this kind of integrals here. So this here is a little bit of a miracle. I mean, it's not easy to get the collision moments in terms of currents like this. I mean, it doesn't happen often, right?
How this is related to the choice of interaction?
Here?
No, the fact, how crucial was the choice of?
Crucial.
In order to get this
yes, if it's not lambda phi 4, this is not true. It's not true. And lambda phi 4, if you want to know the details, it just is 1 over S factor cancels the S that appears. Usually it's S time cross section. So for this choice, you just get momentum independent kind of a transition rate besides the deltas, right? So it makes things very easy much easier than constant cross section even. So this is only true for this interaction.
Yes.
But you have to determine the C.
Yeah, you mean exactly. But that's the thing. So for this interaction, I can write this in terms of the moments, avoiding this F. So everything I try to do here is avoid F, right? By just expressing things in terms of moments. That was the strategy. So I know, in principle, F dependence is hidden in all of these moments. But here I have this kind of relation which, to currents, yeah. So A is a variable like any other variable here. So the variables of this theory is A, J mu, and J mu nu. So I have these degrees of freedom, which are moments, the first 3 moments of F, essentially. And I construct a theory just for these degrees of freedom. F is hidden inside, but I don't need to make any mention of F or any expansion of F to get here. And again, for this interaction, you can do it, the mathematics, right? But not in general. So I guess there's a... Yeah. Yes, the Mandelson variable, yeah. You mean, let me see if I wrote it here. Did I? Oh no. So here, this S times. So this here, this becomes a constant if I choose this interaction, right? Where? Yeah, this. I mean, in non-relativistic, I think example, this is like the relative velocity which enters in the Boltzmann equation. Yeah. So yeah.
For massive factor. Because you have a factor which is, I don't know, yeah. 1.2. This for colliding factors, so it becomes S.
So.
But, yeah. Then I have a question.
Okay. Yes. Mm-hmm. Mm-hmm.
But they end up with a theory that has only and U and TU. They don't have this additional A, which by the way was renders the theory pathological. So I wonder if there is something about the introduction of this degree of freedom A that for some reason they were just like theories about it, even if normally they're something the same equation.
Yes.
They are writing differently the A, U, and the stuff on the right. But they are solving the same system of equation. The divergence of the first 3 moments.
Yes. It's hard to say. Intuition is a very broad, concept. So the thing is, since there is no equilibrium, it is natural that something else appears somehow, right? You need a variable which will convey this information that the system is out of equilibrium and could be, but why this A specifically appears, so again, if you think that I have a theory for the first few moments of the Boltzmann equation, and A is the 0th moment, it's very natural that it appears, right? In this sense, right? So then if you do it, so then you cannot see anything very obviously wrong with this thing here. But why does it have to be this variable, and why does this variable make it unstable? I don't know. The only thing that I did so far was I went higher order just for A, and then I get a kind of second order equation in time, which doesn't seem to be pathological. So maybe just assuming a relaxation, a first order theory for A is just maybe a mistake. It doesn't go to equilibrium by trivial relaxation, exponential damping. But I don't know. I mean, I don't really have any intuition. Yes. No, 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 no. Trace of T mu here is zero. Is zero. Is zero. Yeah. This A has to do with bulk as well. So in the Landau matching procedure, the bulk viscous pressure is m squared times A, right? So over 3 maybe, m squared over or minus, I don't know. But essentially what we usually call bulk viscous pressure, it's m squared times this A thing. So, and when we set the mass to 0, the bulk vanishes, but this field doesn't, right? It's still there, and it will appear here. It just doesn't go away. Mm-hmm. You're right. Yes, yes.
So maybe by A, yeah, but we don't manage any more to play quick, but if you were massless, then A would no longer be.
So you make maybe I can derive a theory where it has a mass and I take the mass to 0 and get a limiting. Okay, maybe. I don't know. Yeah.
I have a question.
Yes.
What happens to the engine? So F log F.
Yeah, so Lorenzo was asking me this yesterday. I don't know. We have to calculate, but one thing that we want to understand is whether this problem here has to do with some sort of pathological behavior for entropy, like negative entropy production, or that maybe there's some relation between. Yeah. So, but I haven't done the calculation. Yeah. The problem is usually when we discuss entropy in Boltzmann equation, we expand around equilibrium, and this simplifies the calculation considerably. If I, in this case, it's more complex. I can calculate some of the terms, but not all of them.
Okay, so I would thank.
Thank you very much.